So now that we have described a few examples of general requirements specified as models, we now talk about different perspectives of model-based documentation, specifically data, functional, and behavioral perspectives. So in general, if you have a different perspective to cover, you have to use different models for your requirements documentation. So in general, you can have a few examples of which diagrams to use for which perspective. These are not strict rules, but as an example, when you have a data perspective to cover, you could use entity relation diagrams or ER diagrams, or you can use UML class diagrams. For functional perspectives, you can use data flow diagrams or activity diagrams, and for behavioral perspectives, you use state charts or state machine diagrams. So the first one is data perspective, and we talk a little bit about what ER diagrams are. So essentially they are a concept that is derived from the world of database or database management. So essentially it's used to model the data or entities and the relationship between these various entities. The extensions of the entity relationship diagrams are basically have been developed over the years, and essentially that results in more extra documentation efforts, like having minimum and maximum notations for the cardinality between your entities in the relationships, and also inheritance of some entities from others, so have like more abstraction inside of your model documentation. And all of these extensions and the nitty-gritties of doing ER diagrams are out of the scope of this lecture course. But we still have a small example. So we already had this example for navigation system. So following the same scenario, on the top right, we have the navigation device, which has an attribute called identification. So the identification of the navigation device. And on the left, it calculates a route. So we have an M to N relationship here, which basically means that many navigation devices can have calculation of many different routes. So there isn't a specific cardinality exception here. And each route has different informations stored inside of it, like distance and duration of the route. And similarly, the navigation device will query the traffic jam information. And this traffic jam information could be about which road the traffic jam is and where does it start and the length of the traffic jam. So just as an example for this kind of scenario. And maybe a little bit different type of relationship. On the bottom, you have the relationship between the navigation device and the vehicle. So generally, most vehicles only have one navigation device. So it's a general scenario. You can have a one-to-one relationship between your navigation device and your vehicle. So moving on to UML class diagrams, another type of diagram used for the data perspective for models. So these consist of classes and their associations. So it's kind of derived from the object-oriented programming model. In principle, these are similar to ER diagrams, and essentially the relation between ER diagrams is that classes are like entity types and the associations are relation types. And these can generally be more powerful than ER diagrams because they have more information on the actual classes, and they are generally closer to the actual implementations that derive from your diagrams. An example of UML class diagrams. So within the same scenario of having navigation, on the top left, you have the route. So as before in the ER diagram, you have the travel duration and the distance. And the navigation device calculates this route, and it also has identification inside of it. And you can have the same relationship from before. You have that the navigation device belongs to a vehicle, and there is a one-to-one correspondence between a vehicle and a navigation device. You cannot have a vehicle with more than one navigation device in this scenario. And this example goes on and on. A lot of the aspects here are the same as before, so it doesn't really have to be iterated. It's pretty self-explanatory diagram. So now we go on towards functional perspectives of model-based documentation. As an example, we have data flow diagrams. So data flow diagrams model the flow of the data through your system. So what data is input and output towards different parts of your system, and what are the recipients of this data. This process can be applied to different levels of abstraction that you have within your system, and requirements on different levels of this abstraction is also possible. So you can have different requirements on different levels. So as an example, in the same scenario, we have a GPS satellite system which provides the location data that is required for calculating the route of your navigation system. And you can also show that the driver is providing the destination as data which flows into the same function that calculates the route. And other information that goes into this is traffic information as an extension. And once you have the calculated route, you have this route data that's generated out of this function. And then this can be piped into determining the next waypoint based on the current route. And if you need to recalculate your route, new route information is added to your main route data. And then this update happens, and then you have a new determination of your next waypoint, essentially. And then you can see how data flows between the different functions, let's say, of your system. So this essentially encapsulates how data flow diagrams can show you a little bit more on how your data is flowing between different of your different functions. Essentially, that's why it's a functional perspective. UML activity diagrams are also used to model the functional perspectives. So you could have it's basically a method to model your action sequences. So sequences of actions happening one after the other. It depicts the control flow between your activities and the actions. It can also include the data flow. So the data flow diagrams that we showed before show you which data is being flowing between your different activities and actions, but activity diagrams do not always show you the data. So as an example, for a UML activity diagram, in the same scenario again, you have the big black dot on the top that indicates that your activity has started. And starting from that, when you start navigation, there are two different processes that can happen simultaneously. So synchronicity of different functions is also an aspect that activity diagrams are very good at. So the user might give you the input destination, and the determination of the current GPS coordinates can happen simultaneously. And once this happens, the system can ask for the desire to calculate the route dynamically. And if the user wants to avoid congestions, there's like a statement that determines which direction the flow of your system is going to go to. So either it queries the traffic info, or it just does not avoid congestions completely and just goes on to calculate the route. And essentially, that's how it works. Once you have the route that is given as output from your system, and that essentially is the whole activity completed in one diagram. So the whole system and the synchronicity between the various controls that happens is all contained in this diagram. Notably, what's missing from here, like we mentioned before, are the particular data that's being handled between these various functions. So now we talk about the behavioral perspective, the final perspective that we are focusing on in the term of state charts. So state charts, if you're familiar with more theoretical computer science, is an extension of finite automata. These essentially support the hierarchization of states. This allows for concurrent behavior to happen simultaneously, and it allows you to synchronize different behavior of your systems happening within the same model. So on the left side, you have the navigation device that is inactive. So essentially the state of the navigation device is modeled into the state chart. So while it's inactive, it needs to first be activated in order for the whole navigation system to start. Once it's activated, within the state of the navigation device being active, if there is no GPS signal, then it has to receive the GPS signal or a valid GPS signal for the whole navigation to be processed. Otherwise, there is no GPS signal, and every 5 seconds, this whole process keeps continuing. So essentially, the state of your GPS device and also the procurement of the GPS data is also something that can be modeled based on states. And once your navigation device is deactivated, it goes back into the state of being inactive. Simple to understand different states that the navigation device can have.